Okay, so this topic is Wheatstone Bridge. Wheatstone Bridge. Now, what is a Wheatstone Bridge? It's an arrangement of four resistance. Find it, four resistance used to determine one of the resistance quickly and accurately in the term of the remaining three. That means, let's say if you have four resistance and in any one of the resistance value you don't know. So you can find out the value of the unknown resistance by knowing the other three. By the using the value of other three, you can find the value of the one unknown resistance. So how to do it? Let's make a Wheatstone bridge circuit. Now consider these are the four resistances. You can also draw at the same time these four resistances and connected to the whole circuit is connected to the cell. So let's name the four resistance as P, Q, R, and S. Now, from this point to this point, I'm going to connect an ammeter. You won't know what an ammeter is. Ammeter is a device that measures the current, and the current is flowing in the circuit. Now, when when this ammeter reading, when this ammeter reading is zero, that is, this reading is zero. Ammeter reading zero means it means that there is no current flowing from here to here. No current is flowing from here to here. So if the ammeter reading is zero, then in that case, this is called a balanced Wheatstone bridge. Balanced condition. This is a balanced condition. And what happens in the balanced condition, that the ratio, okay, the ratio of these four resistance will be P by P. The ratio of these four resistance will be P by Q over R by S. Now look here very closely. These four resistance P, Q, R, S. This will be in the ratio P by Q is equal to R by S. But it is only going to happen if it is balanced condition. And when it's a balanced condition, when the current is not flowing between these 2 points. Okay. So when the current is not flowing between these 2 points, then the ratio of these resistance will be P over Q is equal to R over S. Conversely, if the ratio of the resistance is like this, if the ratio of the resistance is P over Q is equal to R by S, then you can conclude no current is going to flow between these 2 points. You can at the same time also conclude that the potential of this point, and this potential of this point is same. Why? Because there is no current flowing between these 2 points. If it is balanced, if the ratios are matching like this, then no current is going to flow and this will be a balanced condition. Now, let us derive the expression and let us find out that why is it a balanced condition. So hopefully by now you already know Kirchhoff law. So we are going to use the Kirchhoff law here and write the circuit loop equations. Okay, we are going to write loop equation. Now consider this Wheatstone bridge. So you have four resistance here, resistance P, resistance Q, then R, and then S. Okay. So the current is coming out from the cell E, this I current here, and this I current is getting divided into this I1 in this line and I2 in this line. Then I1 current goes here, and at the point P, some current is going to flow here. This current is called IG. IG means the current going to the galvanometer. Now, you don't know what a galvanometer is, that you're going to learn in the next chapter. So for now, just understand that this is an ammeter. Basically, a galvanometer can be converted into an ammeter, that you'll learn in next chapter. So for now, only visualize that this is an ammeter. Basically, this is an ammeter. Now, if there is some current going here, now don't confuse that this is a balanced condition. This is not a balanced condition until now. We are just writing the Kirchhoff loop equations. So if there is a current going here, that this current becomes IG. Now from the Kirchhoff current law, we know that if the current I1 is coming to this point and IG is going here, that means from to here, the current that will go will be I minus IG. I minus IG's current is going to go here. IG current goes here. I2 current was coming from this point, and at this junction D, IG will combine with I2, and here it will become I2 plus IG. So at the point C, again I1 minus IG, I2 plus IG, they will all combine, and eventually here IG will go off. It will become I1 plus I2, which is actually I. So that's your circuit. Considering this circuit, we can write the two loop equations. Okay, we can write the two loop equations. Let's consider the loop BC. Consider the loop BCDB. Okay, so what is the loop BCDB? Let's look here. So B C D B. So I'm going to write the loop equation for this loop. Okay, this loop. So for this loop, if we write the loop equation, what it will be? It will be like this. So what is the current flowing? Current flowing in from B to C is I1 minus IG. So I1 minus IG into the resistance Q. Now you can put this as a negative, because the sign convention which I taught you was the potential drop will be taken as negative. So put this as negative. And from then C to D. So here you see there's a potential rise which is going to happen. Here potential rise is going to happen, and potential rise is going to happen. How much potential rise? The current flowing is I2 plus I2 plus IG, and the resistance is S. So the potential rise that happens is I2 plus IG into the resistance S, and this we are going to consider as a positive value. Okay, because our sign convention is potential rise is positive, potential drop is negative. In this book, there, as I told you before, there are different books following different conventions. You will always follow the convention as I taught. Potential drop is negative, potential rise is positive. And then again, you have to complete the loop equation. You have done BC and CD, so you have to come back to the point B. So coming back to the point B, now you see this device which is for us a ammeter, which is actually a galvanometer. As I told you, learned that in next chapter. This device will have some small resistance. Okay, it will have some small resistance, and because we are moving from the point D to B, you will actually have to cross over this resistance. So there will be a potential rise when you cross this over. Why a potential rise? Because current is coming, IG current coming in this direction. So obviously you see before the resistance, this will be a higher potential, this will be lower potential, and you are moving from here to here. So there will be a potential rise going to happen, and you are going to take this as a positive value. So this will become your loop equation for the first loop. Please write the loop equation at the same time. Okay, write the loop equation by yourself, then you will get it through. Now next we are going to solve this loop ABDA. Okay, so look here again, we are going to now solve the loop ABDA. Now what is the loop ABDA? Look into the figure carefully. This is A, B, D and A. Okay, so this is your loop ABDA, and let's solve this loop with the Kirchhoff. So what are we going to do? We'll start from the point A. Okay, let's start from the point A, and from point A you move to the point B. So from point A to move to point B, from this point to this point, if you move, there will be a potential drop. What will be the value of potential drop? The current flowing I1 times the resistance P. So this will become I1 times P, and this we are going to take as negative value. Then you're going to move from the point B to point D. So point B to point D, you see the current is flowing in this direction, and there is a resistance in this ammeter or galvanometer, and you will be crossing over the resistance. That means you are moving from higher to lower potential. Again, this will be a potential drop. So I'm going to take this as a negative value here again. And then you move from the point D to point A. Now current is coming in this direction, and you are moving opposite to it. This point will have a lower potential, this will have a higher potential, so this will be a potential rise. What will be the value of potential rise? That will be I2 times the resistance R. So it will become plus I2 times R, and this will all become 0. So these are the two loop equations that you have written. Now, when you combine these two loop equations, you will find that in the balanced condition, okay, in the balanced condition, we have just understood that the balanced condition of the Wheatstone bridge is the one where no current is going to flow between these 2 points. Okay, that means the potential of these 2 points should be same. That's a balanced Wheatstone condition. Now, for us, if this loop, if the loop that we have written, the loop equations we have written, if this is a balanced condition, that means Ig value should be is equal to 0, isn't it? The Ig value should be 0. That means the point B and the point D must have the same potential, and there is no current flowing between point B to point D. Ig value will be is equal to 0. That is our balanced condition. So if this balanced condition is true, then how does our two loop equation looks like? So because Ig value becomes 0, so from both the equation, you are going to take out the Ig values. That means from the first equation, you are going to take out the Ig value. You see from here. So this value becomes 0. Okay, then again this value also becomes 0, this also becomes 0, and then in this expression again the same thing, this value becomes 0. So you will end up in having these two equations for the first and the second. These two equations you are going to get, because Ig becomes 0, and again why it is becoming 0, because we are calculating for the balanced condition, and under the balanced condition there is no current flowing between those 2 points. So your two loop equation will then look like this, and then you divide it, you will get this value as P over Q is equal to R over S. So that is the balanced Wheatstone condition. Very, very important topic, and most questions that you are going to get from the Wheatstone is either to find out whether the Wheatstone bridge is balanced or not balanced, or it is already given that the Wheatstone bridge is balanced. That means the potential of these 2 points are same. Okay, potential of these 2 points are same. Now if the potential is same, no current is going to flow, and whatever you keep, let's say you keep a resistance here, this resistance will not be active in the circuit. If you keep a capacitance here, again that will not be active in the circuit, because the potential of these 2 points becoming same means no charge will flow, no current will flow, and whatever you keep in between will not be active in the circuit. So that is your balanced Wheatstone condition. Now, Wheatstone bridge. Wheatstone bridge is a very useful device. I mean, the useful setup in the lab condition, in the experimental lab condition also. So in the experimental lab condition, this Wheatstone setup is done on the meter bridge. I hope you remember what a meter bridge is. We discussed it when we did a potentiometer. Remember potentiometer? I taught you that there is 1 meter long scale. You will find it in your experimental lab in your college. You will find it, and that is basically used, and that 1 meter long scale is converted into a potentiometer. So now we are going to convert the same 1 meter long scale with a wire upon it, that is a meter bridge, into a Wheatstone bridge. Okay, so we are going to use it for a Wheatstone bridge setup. Now, how to make the Wheatstone bridge setup? We're using a meter bridge. So look into this diagram. Now, this is your that meter bridge. As I told you, this is the 1 meter long scale. Consider this is 1 meter long scale, and upon the scale you will have a thin wire. Okay, thin wire passing over from the two ends. The total length here will become 100 centimeter, as it is 1 meter long scale. Okay, and then you have, look very closely, you have two resistances here. One resistance is here, which is R, and there is a word written here RB. RB means resistance box. Resistance box. Resistance box is basically a box. You will see it in your lab again. Resistance box, and there are many different resistance value that you can use into it. Okay, so you can change the value of the resistance. It's kind of a variable resistance. You can change the value of resistance here in the resistance box. So this is something known to you. Okay, this is something known to you because you know the value of resistance box, or whatever value you put there, you know this value. Now let's say this resistance here S is unknown. Okay, this is unknown, you don't know this value of S. Okay, you don't know the value of S, and this is your meter bridge. As you can see, this is your meter bridge. Now, previously also you have learned that the resistance of any resistor is proportional to the length, isn't it? The resistance is proportional to the length. In the potentiometer we have then resistance proportional to the length, potential drop also proportional to the length. Here we are going to use the same principle. How? See, first what we have to do, that pick up a point between these two resistance here R and S as a point D. From this point I'm going to connect one wire, okay, one wire, and pass it over with a galvanometer or again an ammeter with a small resistance box here. Okay, now what is the purpose of this resistance box? Simply show that if the current is flowing, it should not become a short circuit, so you just have a small resistance here so that this 2 point doesn't become a short circuit condition. Okay, so now then what we do is to find a null point. Remember what was the null point? Null point was a point on this meter bridge where the reading of this ammeter or galvanometer, the reading becomes zero. Okay, so we will have this setup from the point D, again a wire, resistance box, and a ammeter, and this jockey I'm going to slide over this meter bridge. I'm going to slide the jockey on this meter bridge, and I will find a null point. Null point, again the point where the reading of this ammeter is zero. Now, when I find the null point, that means that these 2 points, that is point D and the point B, where I found the null point, no current is flowing in this line. That's the null point. Means that this point and this point will be at the same potential. Very simple. And that would also mean that this setup will now is a balanced Wheatstone condition. This is a balanced Wheatstone condition. Now, in the balanced Wheatstone condition, we know that the ratio of the resistance should be R by S. That means this resistance by this resistance must be is equal to the resistance of this length of wire AB. Okay, this resistance here, this one is to the resistance of this length. Okay, that means I can say that the resistance of this length AB will be proportional to the length L. Why? Because I know that the resistance is always proportional to the length of this resistor. So here you see this resistance will proportional to the length. So instead of the resistance itself, I can write here L, and then the resistance BC will also be proportional to the length, and the length here is 100 minus L. If this is L, this will become 100 minus L because the whole length is 100 centimeter here. So it will become 100 minus L. Now L you already know because you have found out the balance point here. So the length L you already know, and 100 minus L also you know, and this R here is also known to you because this is what your resistance box resistance is. So this unknown value S you can find from here. Okay, very simple topic, and this balanced Wheatstone bridge experiment is there in your PU exam also. The next is sensitivity of the Wheatstone bridge. This is also very simple. The sensitivity of the Wheatstone bridge is very sensitive. That means the Wheatstone bridge will become very sensitive if the resistances that you are using, P, Q, R, S, all those four resistances are of the same order. Relative magnitude of the resistance in the four arm of the bridge. The bridge is most sensitive when all the four resistance are of the same order. Same order means they are have the value which is nearby to each other, not like one resistance is like a 100,000 ohms and the other resistance is 1 ohms. Okay, that's not the same order. Now again, in the balanced Wheatstone condition, this is also an important property of the Wheatstone bridge, and you will find such question in your JEE Mains paper or JEE Mains type of questions. You will find uh, if the bridge is balanced, then on interchanging the position of galvanometer, that is the ammeter again in our case, and the battery, there is no effect in the balance of the bridge. Now, what does it mean? It means that if you have this Wheatstone bridge, okay, if you have this Wheatstone bridge and this is your battery, and this is where you have connected your ammeter or galvanometer. So if I, for example, let's say if I change this and if I put the battery here, okay, and then I put the ammeter here, then again this will be a balanced condition. Okay, that's again it will be a balanced condition. You look at the circuit once again, you will again find that this will be a balanced Wheatstone condition, and that is why, They are called the conjugate arm of the bridge. Okay, so if you interchange the battery with the ammeter, interchange this, the balancing condition will be still followed.